So somebody, who was it that gave us the donut idea? Was that somebody here? Or was in the 700 level class? So we were talking about donuts. Very appropriate, actually, eh? That's all we ever do, it seems. And they said, oh, well, there's this really cool program that looks like this. This here should have been indented a little nicer here at the top, but otherwise. And if you compile that, gcc-o donut, then you get a whole bunch of warnings, but that's okay. And then you say donut, and then you get that. It runs so much faster in C, doesn't it? So we thought, well, we can do this in espresso as well. So we did. And oh, well, here's the Java version. We not oh, I just called the donut a Java, right? So there is the espresso version, and it needs this arrays thing. So I posted it on Yab, but nobody seems to be reading Yab. So if you look in include, I put in arrays.java, which are just those two, and in lib.java I put them in like this and compiled them, and then we should be able to say espresso donut.java, and just to see the code we get, it looks something like this. So it's not super long. Let's see, 375, but we should be able to Jasmine that, and then we should be able to run it. And what do? See, there it works. Now, of course, that wasn't enough. Then I went home and I'm thinking, now I know how to do ASCII art. What can I do? And then it turns out you can do this. So I went home and started implementing Pac-Man. So here we have, this is very close to running in Espresso. I just got to do a few little fiddly things. And then I got to program the ghosts. But otherwise, we now have we have Espresso Pac-Man. All in the terminal. It's kind of pathetic, but it's kind of cool. Well, no, Matthew, I didn't actually. They happen sometimes, and that's why I haven't tracked them down yet. They don't always happen. So there's some collision issues and some ghost movement issues, but that's about it. And that's sort of the length of it. So WC pacman.java, under 400 lines. This does require a few tweaky things where you need to be able to call synchronized methods in order to put locks around who has access to updating the screen. And that can be done. It's not very complicated at all. It's a little bit of a hack. It needs multi-threading, which Espresso fully supports through the thread library, which is already installed in your handout, as it is. And that's about it. I got to fiddle a little bit with the Unicodes because Jasmine is not fond of Unicode strings, but it doesn't mind Unicode characters. So there's sort of a workaround on that. But I think that's pretty kind of cool. But anyways, that's what I wanted to show you. And then we should do something else. Now, are there any phase 6 questions we need to deal with first? I suppose we should have done that while I had the terminal up.
I had one, if that's all right, Professor.
Mm-hmm.
So I'm finishing up reading chapter 8, and towards the end for the code generation, like for visit if stat, you
Yeah.
have these strings leave true and leave false, and I can't find them in the or any kind of thing similar to it in phase 6. And I was wondering if there's some kind of substitution or something we could
Well,
do.
so are we looking on page 617? No, wait,
Uh,
we're not. Where are we at?
626.
626. 626, that's an optimization. That can't be right. Hold on. I'll have to, we have to look in a real book. 626. 626 if statement. So 626 is so what's the problem there? This is for as an example to do with that little language thing, right?
Yeah, so I'm just like wondering if there's something that we should be keeping track of in ours like that, like a previous leave true and leave false, or
No, you shouldn't because I think this one, if I'm not mistaken, is implemented with the smart jumping. So with where the if statements or where the expressions will not leave 0 or 1 values on top of the stack, but it will jump. And remember, we talked about last time, we said it's much easier if we do. So let me just sort of try to illustrate. If I have something that looks like so if we just wrote something like this, right? If I were to handwrite that, I would be able to do so. So if we handwrite it, and let's say that I lives at address 1, J at address 2, J at address 2, and let's say they're both integers. Then I could do something where I say I load 1, I const 2, and then I can say if underscore ICMP LT, go to L1, put L1 here, say I const 4, actually, let me redo that. CMP, so I'm going to say GE because that way I can jump to the else part, L1. I const 3, I store 2, go to L2, L1 is I const 4, I store 2, and then put L2 there, right? So I'm using sort of the opposite operator here. I'm doing a greater than or equal, and if it's greater than or equal, then I jump to the else part. And if it's not, then I fall through and I do this part here, right? So here I'm using the fact that this operator here is going to leave on top of this, so it's gonna jump when I use if ICMPG. But what if I had written code that looked like this? K equals I less than 2. Then now all of a sudden I need this to result in either true or false, and we'll say that true is a 1 and false is 0. Well, how would the code have looked now? Well, it would look somewhat similar to the code we have up here. We just have put a 1 there and a 0 there, right? So sometimes you need Boolean expressions to be a value, and sometimes you need them for jumping. And it's rather complicated if you've read the code about the jump code section, the evaluation or the code generation of your Boolean expressions will have to know whether or not they're involved in something that requires them to jump, or whether it's involved in something that requires them to put a 0 or 1 on top of the stack, right? Because if I look at the code that I need to generate for this, well, that's going to look like this completely. But what is the code going to look like for this if I'm using it in a jump? Well, then it's only going to be those 2 lines, right? So it's rather complicated, and when you get these nested and negated and anded and or, it just becomes complicated to a point where I haven't actually even tried implementing it myself. So the easiest way to implement a Boolean expression is to say, right, all Boolean expressions evaluate to a value, just like any other expression. So it's going to leave on top of the stack a 0 if it's false, or a 1 if it's true. So for a binary operation, E1 sum op E2, we should be able to generate some code that looks like this. So code for E1, code for E2. If, so we're just going to do this for integers now, if ICMP something 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 L1, put L1 here, iconst 1, oops, go to L2, iconst 0, L2. So if I always generate code that leaves either a 1 or a 0 on top of the stack, then if I come back to my if statement, I know now that when I execute the code that gets generated for this, there will be a 0 or a 1 on top of the stack. So now I can write some code that says, well, this part here was for I less than 2. And if we're going to do that right, then we'll say if GE there. We'll go back and see if this is exactly how I generated in a second, because I can't remember if I negated or not. But if you wanted to keep, if you didn't want to negate this one, and you wanted to do exactly the one that we have, then we'll say GT, go to L1. L1 should then do the 1, and this guy here should do the 0, and then we'll get rid of this thing here. Either way, it doesn't matter. You can negate the operator and swap these around, or you can use the operator as is, and then these have to come in reverse order. Right. So if I want to finish this off now, this now takes the place for this stuff here, right? And now I'm going to have to say something like if EQ. So that tests if the thing on top of the stack is equal to 0. If it's EQ, then we'll jump to L3. Else we'll say I const 3, I store 2, go to L4. We'll put L3 here. Say I const 4, I store 2, and put L4 there. So we know that every time we have visited, or every time we generated code for an expression of Boolean type, when it's done running, it will leave a 0 or a 1 on top of the stack, which means that all your looping relies on the fact that there's a 0 or a 1 on top of the stack after the Boolean expression has been evaluated. Does that help?
Very much. Thank you.
Yep. So let's actually just try real quick here to let's just move my Pepsi so don't spill all over my iPad. let's see. Can we just look in the Pacman code and see if we didn't generate that? How about oh, we have an if statement in here. We have a while statement in the constructor. So there's a constructor. Right, so here we go. Let me just look at the code again. This one says x greater than 0. Grep has to be that. Test 15. J. Yeah, so it does GT jump to L3. L3 is 1, and the other one is 0. That's exactly what we did on here. Yeah, so I've used the operator as it is, and then swapped the 0, 1 case, right? So if that is true, we jump down here, put a true on. Otherwise, we put a 0, which is false, and jump around it and end up there. And then we use if EQ to jump out if we're done. So that's there. If not, then we'll do the body of the loop. Right. So that was right. Right. Anything else? Right, then I think we were at 926, which is dead code elimination. And let's just let's start with a definition here, and it's going to be 9.1. And what we're going to do is we're going to go back and look at our basic blocks in our. Does this look like this? Why is this not bigger? I'm confused. Can you actually see the screen? Why does this look like this? Normally it doesn't look like. Normally it doesn't have that black stuff around. Huh? Does it? What do I know? All right, cool. All right, so we're back to look at basic blocks. So if I say that a basic block B is dead code if code in B can never be executed. I.e., which you should only write if you're inside of parentheses, that is, there is no path in the control flow graph from B0 to B. So we can't get there at all. And any dead code can be removed. So basically, we don't have to put that into the file. Now, let me just see if I can take a picture. I don't want to have to draw all this stuff. Let's take a picture of this stuff here. So here's some code. We'll use that. Put that there. Just crop it a little bit, maybe. There. And I'm not going to bother showing you the actual code, but I will see if I can figure out, why is it my fingers are always in the way? Take a picture of that. Yeah. And we will crop that as well. There. 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 Put it there, and we'll make that a little bigger. Right. So if we look at that code, then of course we can just do what we normally do, and turn. I suppose actually, let me see if I can photo that in as well. I think I probably can. There, yeah. That'll do the trick. We just need to crop that a little bit. Good enough. We'll make it a bit smaller, put it there. Right, so we can go from there to there and there to there. Now, if you look at this code, or this graph, this control flow graph, then are there any nodes in that control flow graph that cannot be reached from B0, which in this case is labeled A? Benjamin says K and M can be eliminated. Yes, K and M can be eliminated because they are not reachable. So these, or should we do that in red? These cannot be reached from A. So sometimes when we draw these graphs, we have a graph that consists of two parts. So not everything is always connected. So it could very well have been that K pointed to M and M didn't point to anywhere at all. And some people make the mistake of saying that if the graph is fully connected, not fully connected, that's not the right word. So if the graph consists of just one component, then you can't eliminate any code. But that's not true, because there is just no way to get into these, because if you look at this arrow, it points away from M. So you can only get to M from K, but there's nothing that points to K. So how do we figure out if I've been given a control flow graph, which nodes, i.e., which basic blocks can be removed? So now we dig back into our graph algorithms and think, which graph algorithm can I use to determine which nodes can't be reached? Really? Not reachability? Wasn't that what you said?
No, I said branch.
What's that?
It's just
You don't need to make it complicated. You just color the graph, right?
you just make a tag.
So, well, that's what it is. So let's color this thing, all right? What's your favorite color? Purple? So we start here. Actually, that's not a good color. We're going to have to go highlight a color. Oh, they have a purple as well. So dirty purple. We'll get that one, right? Michael says the line before it has a go to instruction, and the line itself doesn't contain a label that can be jumped to. That's true, but that requires you to go and look at the code. What we're going to do is we're going to find a way to actually do this by simply coloring this graph, right? So if I've created the graph, I can start from A and say, all right, where can I go to? I'm going to color all the nodes that I can reach. And I'm sure you remember, did you remember the graph coloring algorithm? The one where you say, right, when I get to a node I haven't been to, I'm going to color it. And then I'm going to take all its children that haven't been visited and put onto a queue. And then I'm going to take the head off, visit that, and color it, and take all the children that haven't been colored and put them onto a queue. And at some point, that's going to terminate because we've now visited everything. So we'll get B on the queue, and then we'll take it out, and then B will put C and D on the queue, and we'll take those out. C will put E on the queue and deal with that. So actually, we should have done that in that order. So that'll visit this guy, which will 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 visit this guy. which won't do that one, which will do this one, and then we'll come back, we'll do that one, and that one, and now my queue is going to be empty, and I'm going to be left with these two guys down at the bottom that cannot be colored. And this is not the coloring algorithm we did last Tuesday. The one we did last Tuesday was somewhat more complicated because it required us to alter the graph. Remember, we said, or hey, pick something, and we said pick the one with the lowest degree, and then color it certain, whatever color you've gotten to in your palette, and then remove all its neighbors, both nodes and edges, and whatever edges were sort of like pointing out into nothing after you've done that. Then now pick the one with the lowest in degree again and color that the same color, and keep doing that until you eliminated the graph. Then reassemble the graph, pick a new color, and play the game all over, and keep doing that. So it's a much more complicated coloring algorithm than this one. This is simply just reachability in a directed graph. So yeah, that's the easiest way to do it. Is just color the things you can get to. And of course, when you look at this graph, you probably don't have to pull out your crayons, right? You can look at and say, yeah, what's suspicious here? The only thing that isn't pointed to is K, so anything K points to that isn't pointed to by anything else can probably be removed as well. So it's pretty obvious that the dead code here is K and M. So that's it for dead code elimination. It is super easy. There's not much to do. So now we're on 9.3, which is bytecode analysis. And we'll talk about a couple of them. We're going to do 9.3.1, which is I can't spell uninitialized. Should we try that again from the beginning? I don't understand until this day. If I have to spell a word in English, I have to do it in Danish. I cannot spell an English word in English and get it right. I have to spell it with Danish letters. And then I don't know what's going on. Yeah, I feel like that often. So, for example, if I said, we've already talked about this, so this should be fairly easy. So there's some stuff in here where there's no assignment. To A. B gets some value. If B is greater than 10, then A is 100, and C is A plus B. So if I look at this code, then we might get something that looks like this: by push 10, I store. Why does it look like that? Oh, by push something. I don't know what that is. That's just some value for B. We'll do that, and then we'll say I load 1 by push 10 if I CMP GT jump to L2 I const 0 go to L3, there's L2 I const 1 L3 is going to say if EQ go to L1 I push 100 I store 0 L1 I load 0 I load 1 I add and I store. And if we quickly turn that into basic blocks. I think we get something like this. So B0, B1, B2. B2, B3, B4, B5, B6. And if we do the control flow graph, B0. Wait a minute. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Why do I have 7? Oh, I shouldn't have had that one. And we'll fix this by simply calling that one B1. Haha. B1. B2. B3. B4. B5. And B6. There we go. And if we compute live sets here, I mean, if we look at this, we can see that where am I using A? A is at address 0. I'm doing an iLoad on 0 there. So the question is, can I get to B6 without ever having done this iStore here? And that iStore is in B5. So can I get to B6 without doing B5? Yes, I can just go that way. I can go this way. So if I compute live in sets, then we get that the live in set at this point here is equal to address 0, which is the A. So simply by doing a liveness analysis and then looking at the live in set for the very first instruction, if that live set is not empty, then anything that's in there could potentially be used without having been initialized. So we can say any variable in the live in set of the first instruction in the first basic block can be used without being initialized. So also another fairly simple thing to do, especially if we have our control flow graph and that we've already done our live analysis. So easy as well. Now for something that we haven't really talked about, well, I've sort of hinted at it, which is stack analysis. So let's say, for example, if I say something like A equals B plus C plus D plus E. Now, this can be a little bit dangerous to do based on the source code, because depending on how you translate things into machine code or into bytecode, we really should be looking at the bytecode for that. So if we translate that and look at that, then we have I load 2, I load 3, I load 4, I load 5, I add, I add, I add, and I store. Now, if we wanted to, we could sort of mimic the stack. So let's just see. Let's see what does the stack look like. Let's do that in green. So in order to do this, at the point of this, the stack here is going to be just a B. What's the stack going to look like after this? Well, it's going to be a B and a C. What's the stack going to look like after this? Well, it's going to be a B, a C, and a D. What's it going to look like after that? A B, a C, a D, and an E. And then what's it going to look like after that? It's going to be B, C, and then one value, which is D plus E. And after that second IAD, it's going to be B, and then it's going to be C plus D plus E as one value. And then that second add is going to be one value, B plus C plus D plus E. And after that, I store nothing. So if I look at this and I say, what's the size? Well, there's 1, there's 2, there's 3, there's 4, 3, 2, 1, 0. So if I look at that, then I can just ask, what's the max? Well, that's 4. So in order to execute this code safely, I need a stack of size 4, right? Now, we could do this in a slightly more general way, because I don't really care that I'm I-loading something from address 2. What I really care about is the fact that there's an integer on the stack, and after the second instruction, there are 2 integers on the stack, and after the third instruction, 3 integers on the stack, and after the next instruction, 4 integers on the stack. And then after the next instruction, which is an IAD, well, what does IAD do? Well, it takes off 2 instructions, two integer values, and puts another on. So it has a net effect of -1 integer on the stack. There we go. And this one will do that. That will do that. And we end up with this. And again, we can just say, right, this one here has 4 ints. So we could do the following. We can say we could sort of do a table. So if I did iconst1 and the stack before looked like ... well, then the stack after looks like it did before, but it now has an integer on it. If I do an iLoad of any kind, the stack before, stack after will now have an integer. What about IAD? Well, if I have to do an IAD, the stack definitely has to have 2 integers on the top. And then afterwards, I'll take those 2 off, add them together, and put 1 on. So if I look at this, I can see, right, in order to do an add, my stack has to have 2 integers on top. And then afterwards, I will remove those 2 and put the result up there. So basically, I could now go through my entire instruction set, all however many hundreds of them there are, and you would get what I have in table. Huh, I screwed that up. I put the table number at the bottom. That's not right. Table numbers go at the top. My bad. How does nobody not catch that? I'm going to have to sort that out. All right. So this is table 9.1. And we can see that we use I for integer, J for long, F for float, D for double, L for reference, V for any 32-bit value, W for any 64-bit value, and X if it's an instruction that if it's the size that's determined by the instruction. So let's look at what we can do then now. Let's write some, not some Java code, but some Jasmine code. What happens when I run this code? Yeah, Benjamin, that table. Did I fix it? Maybe I did. Let's see. I did. You should have a table caption that's at the top of the table where it should be, but it has a period on. Table captions do not end in periods. Figure captions do. Infinite loop, yes. Infinite stack loading, yeah. So the stack is not infinitely large. So what's going to happen when this runs? Well, yeah, it's gonna blow the stack. I mean, we can try. We'll just use this file here because it has all the stuff that we need. Don't care about the. Suppose that has to be there. We'll yank out all this stuff. Don't want that one. Don't want that one. What? There's no method? No main method? Be a main method somewhere. No? We'll steal that one. Steal the one from here. Ooh, there we go. We'll take that. Put that there. Say end method. We don't need that either. We need that. We don't need this. Yeah. And then this guy here will say limit locals. We'll just do 2. And then I'm going to say I push 100. I store 1. L1. I load 1. Go to L1. There we go. Then we just need to Jasmine that. Missing argument for instruction go to. What does it mean by that? 21. Oh, because it doesn't like that. What? There we go. Now we run it. And where does it know? Oh, it's a lowercase test. There you go. And then it comes out and says, unable to initialize main class test 51 caused by Java line verify error. Class test 51 method main signature, blah, blah, blah. Inconsistent stack height. 1 is not equal to 0. To which you can only really say, no shit. So now, how do I stop sharing this thing? We'll do it this way. Back to there, but now I gotta go pull up the Right. So let's just throw together a control flow graph for this stuff, and do some looking. So we're gonna have by push 100 I store 1. Like that. And then it's going to be L1 I load 1 go to L1. Right. Put that there. Throw a box around that. There we go. And we know the control flows in this way, and back that way. Right. So here's what we're going to do. We're going to play this game just like we did here in the alternative fashion. We're going to just pretend that we're executing the code without caring about what the actual values of variables are. We're just going to look at the types, and we're going to use the table to figure out what it does to the stack. So we can probably all agree that I start out with an empty. We start out with an empty stack. Now, what happens to the stack when I do a by push 100? Well, an empty stack with a by push 100 gets an integer. Well, I store, and now we also got to do some checking, right? Because we got to check that our code is not doing things that it's not supposed to. Because if iStore needs to execute, then it needs an int, or when iStore executes, it needs an integer on top of the stack. And we know for a fact that it has one of those. So we can say, yep, we are in a state that's safe to execute an iStore. Now, what happens to the stack when I execute an iStore? Well, I take whatever is on there away, right? So we're going to leave this basic block with an empty stack coming down here. Now what? Well, we're going to load an integer on here. Yeah. And then we're going to go to doesn't change the stack, so it's the same, which means that we leave this thing with an integer. Now, this is already a problem, right? Because what's going to happen? What do I have here? When I go into this block, I have an empty stack if I come from up here. But if I'm coming from here, I go into that block with a different sized stack, with a different looking stack. So I have an integer, right? We can play this game again then. What happens if I come from here and then I just go through there and see what happens, right? Well, I had an integer on, now I put another one on, I get 2. Right, so that means I have that. You can try one more time. The nice thing is that we don't have to try one more time, because this would not happen if those two were the same. So if we are in a situation where there are multiple flow-ins to the same node, and I have the same stack on all those flow-ins, then we're good. Nothing bad happens. But if they're different sizes, then that's bad, because we can get into this sort of infinite loop thing where we just have a stack that grows and grows and grows. And it's in all its gory details written out how to do this. You know, if you wanted to go and implement it, it's really not. It's not complicated at all. Once you get this idea that what you're going to do is you're going to mock execute the code, but not with real values, and you're going to look at all the branches, and basically you're just going to fill an imaginary stack, not with values, but with types. Now, why do I do it with types? I do it with types because not only can I check that the right thing will be on the stack. I mean, if we go back to our example, here, and let's say that I change that to an F store, I can guarantee you Jasmine is going to be more than happy to compile it. And when I try to run it, it says here, verify error, expecting to find a float on the stack. Right, well, if I go back here and I change this to an F, then we can see that when I do, if I go back and look at what should F store look like here, well, it should say something like ... and then an F, and then ... right? So I would expect the top of the stack to be an F in order to do an F store. It's not, it's an integer. So therefore, we can produce an error when we're verifying this code to say, hey, this code is never going to run because we're not in a situation where I can store a float because I have an integer on here. So in order to do those kind of checks as well, i.e. that the stack is in a mode or is configured in a way that can be always useful for whatever's the next instruction, we differentiate between the various types. But also remember that doubles and longs are 64-bit values, so they take up 2 spaces on the stack. Right. That actually means we are at the end of the book. Conclusion ends on page 666. That means we're done. Okay, so Mesam says, but there could be many exceptions to this, like casting. No, there couldn't. Because if I write code like this, int x equals 1, double d, and I say d equals, actually the other way around should probably be better, double d equals 3.14, x equals int d. Then the equivalent code is going to say LDC 3.14 D store. Well, let's say that's at 1, and let's say that's at 2. D store 2. D load 2. D2I. I store 1. Now, let's just see LDC with a double value. We have D store, D load, D2I, and I store. Doesn't matter what the stack looks like before, but afterwards it definitely has a double on. D store will require a double. That double is gone afterwards. D load requires nothing, but afterwards has a D. D2I requires a D, and after we'll have an I. And I store requires an I, and afterwards we'll have nothing. Right, so let's go. D. Right, there was no requirements. D store requires that there's a D on the stack. There is. Take that off. All right, I can do that. D load requires nothing but leaves a D. There we go. D to I requires a D and leaves an I. There's the D, so we're good to go on that one. Take it off, replace it with an I. Good. I store requires an I and removes it afterwards. And there we go. So we can also see that this doesn't change the stack at all, which is good. We didn't leave anything on the stack. Well, the stack is not the same before and after casting at all, right? Because it changes types, right? It goes from a double to an int because that's what D to I does. And this code, this works because I've just gone through, and if you look in section in table 9, was it 9.1? I think it is. If you look at that one, you will find all the instructions in there for the entire machine. I mean, there's some funny ones. For example, there's dupe 2x2 that has an awful lot of different ways of working. For example, it works on a stack that has v1, v2, v3, and v4. And these are 32-bit values. If I do that, then what I get afterwards is v3, v4, v1, v2, v3, v4. It could also work with two v's and a w. If I do that, then I get w, v, v, w. W is the 64-bit values. It could all work the other way around, a w, a v1, and a v2. If I do that, I get v1, v2, w, v1, v2. And finally, w1, w2, w2, w1, w2. And dupe 2x2 duplicates the top two 32-bit values and inserts them two 32-bit values down, or duplicates the top 64-bit value and inserts them below the two 32-bit values below that, or duplicates two 32-bit values at the top of the stack, inserts them below the 64-bit value under that, or duplicates the top 64-bit value and inserts it under the 64-bit value under that. So this has 4 different forms, but when you get to this instruction, you can recognize the stack to be in any of these 4 configurations, then you know that if the stack looks like that, then it's going to look like that afterwards. If it looks like that, it's going to look like that afterwards. If it looks like that, it's going to look like that afterwards. And if it looks like that, it's going to look like that afterwards. So not only can we do these checks here now to see if we get stacks that are the same, but if I do, then I will have now decorated my entire control flow graph with sort of generic sizes or generic stacks. Well, what's the biggest stack that I need? Let's go through and find the one that has the largest size. So this is a bad example because this one is going to blow the stack. But if we did this for a stack, let's see if I have an example here that we could look at. Oh, there is. It's a pretty large example, so we're going to bother typing it in. But you can. It's example 9.4, and all we do there is we just look at, go through and do this, and we say, okay, fine. At some point, what is the biggest size of the stack? Once I've decorated all my instructions, I can just find that one, and then I know that the .limit stack, which we just call 50 now, could be replaced by that whatever number that is, taking into account. No, yeah, that's fine. Yeah, that's all there is to it. I was about to say something about this, but that's not there. It's on the other stack. So, a few practical things. Come back on, what is it today? Tuesday? No. Come back on Thursday. Yeah, come back on Thursday, because we'll tell you some secrets. Right? We still have donuts, by the way. Have we? Have we got donuts left? How are we doing? One of the Boston creams is mine. Oh, there we go. And we've got that big ass one. So if anybody's around that can eat a half-foot donut, now's the time. And apart from the secret, on Saturday at 2:00, I've scheduled a review session. I don't know what the point of the review session is, but it seems to calm people down because all the old exams have been posted with answers. The ones that have middle fingers and are crossed out, you can just forget about. Or so if you think about it, if there's a question that says something backpatching, and you're thinking, well, wait, backpatching. What's backpatching? I've never heard of backpatching. Well, because we've never done anything about backpatching. I wonder if the word backpatching even exists in the book. Let's see. It does not. So if you cannot find a reference to backpatching in the book that you use for the course, probably because we didn't do it. So you can skip that question too, right? And to answer all the obvious questions, is the exam going to look like the practice exams? Well, it would be very cruel if it didn't, wouldn't it? Funny, but cruel. So yes, is the answer to that. Those who are registered with the DRC people, if I get them to send you a message, if you will, regardless of whether you send me a message or not, it's probably safer to send it to Ben because he is the he's very good with this web campus thing. So if you are DRC registered, then and you need you've requested and gotten approval for extended time, send Ben an email and let him know what that extended time is, and he'll put it into the system. Take it from there. Office hours tomorrow. Yes, Saturday web is through WebEx, like the class is now. I've already scheduled the thing. I've also scheduled a final exam. So show up a few minutes earlier in this room that we're normally in. And if I'm awake, because I'm going to be in London, and it's going to be midnight, if I'm awake, I'll be there. Otherwise, Ben will take care of you, but I will try my hardest. And since Ben hasn't seen the exam, he won't know any of the answers to any of the questions you might have, so there's no point in asking any of them. Right?
Just ask.
Yeah.
Ask yourself. Really shouldn't be.
So Michael says, is the review session recorded? No. I don't think it is. I mean, how far do I really have to go, right? I mean, yeah, I think so. I think so too. Yeah, life's hard, unfortunately.
Patrick, you'll be fine. You're a smart kid.
Ben says, stop whining. The practice exams have been on the website since the first day, along with answers, sort of. When we did these last year or 2 semesters ago, I think, and I put them up. The answers are the shortest possible answers because that way we don't have to read very much, which means we can mark them fast, right?
I want to adopt the edge strategy. If you write more than like 2 sentences, it's an automatic 0.
Well, so in the good old days when you had paper, there was only so much room, right? Except for when there was a new page, and then there was a whole page, and people thought fill it in, right? So blank space is not an invitation for a brain dump or of any other kind of dump.
What's the answers? A vocabulary.
Well, no, I wouldn't go quite that far, but it's not far off, and we're pretty good at spotting bullshit. How long is the final exam? 2 hours.
120 minutes. No.
And it's scheduled. We've scheduled it. Oh, we just need to look at. We need to look at that. Make sure that we did that right. Remember the problems we had last time. The fact that after 2 hours it cut off, and then we set it to 6:05, and wasn't there some problem? We'll just double check it. Yeah. I said that if you score better than the midterm, then the final becomes 50% on the grade. Yes.
Technically not.
What?
It's the weighted values. So if what you score on your final is better than
No. No. If you score 60% on your midterm and you score 61% on your final, then your final counts for 50% rather than 40%, and your midterm counts for 0 rather than 10%.
Oh, that's easier.
It is easier. Except CSGFMS never understood that. And people are like, CSGFMS says that I passed. Yes, but I say you don't. Well, that's unfair. Yeah, life sucks and then you die. And I don't know if Ben says he can make Canvas understand. So I guess that means he can make Canvas understand. That's how it works. Yeah, and again, the Canvas Whisperer. I think it's more like the Canvas Yellerer. Whisperer, yes. Like, here comes my Nordic heritage. I can't tell the difference. But I had a friend who could not tell the difference between B's and W's.
Yeah.
So he could not say very, very well. Because
Like
all
very,
V's.
very
No, very, very well. Yeah, all V's turned out into W's, right?
So
And it's
very,
very, very well. But you try saying fem flade flødeboller på et fladt flødebollefad and see how you do.
Leap flop. No.
Moo? That's if you don't know whether to say yes or no.
No, it's just moo.
Moo?
Spherical cows.
Oh. Right. And with that absolute nonsense, we are out of here for now, I think, because now things are just getting silly. Live setup and instruction is the same as a live inset. Yes, it is. Yes, it is. All right. We're going to eat some more sugar and see where it takes us. See you in a couple of days or tomorrow. Bye. Look, it captions.
Mm-hmm.
Although it says we're going to use some more service, I said we're going to eat some more sugar.
Can't all be perfect.
Oh, but this is pretty darn good. Although it says we are going to use some more service, I said we're going to have to use some more sugar. Eat sugar. Goodbye.